The simplest class of organic compounds are called hydrocarbons. A hydrocarbon is a compound composed only of hydrogen and carbon, much as the name suggests. A hydrocarbon that contains only single bonds is said to be a saturated hydrocarbon, and these are called alkanes. All alkanes end in the suffix ane, A-N-E, and generally have the formula of CnH2n plus 2. So for example, methane ends in ane, so we know that it is a saturated hydrocarbon containing only single bonds. Meth means that it's only one carbon, so we would have C1H2 times 1 is 2 plus 2 is 4. So methane's formula would be CH4. Propane ends in ane. We know we have a saturated hydrocarbon. Pro means 3, so C3H6 plus 2 is 8. Structural formulas for alkanes can be written as such, where they'll always have a methyl group at the end and a methyl group at the beginning. And in between, you'll have repeating bonds of CH2 over and over and over again. Alkanes are often called straight chain or unbranched hydrocarbons, but we draw them as zigzags because of the 109.5 degree bond angle between carbons. And again, we can see that that would be a 109 degree bond angle because of the tetrahedral geometry carbon adopts when it has 4 bonds. Because they contain only carbon and hydrogen and all in equal amounts, all alkanes are nonpolar. And their only intermolecular force are Landon dispersion forces. And because of this, alkanes have very, very low boiling points and melting points. For example, methane and ethane are both gases. Propane is a gas that you use to burn in the lab on your Bunsen burner. Butane also is a gas that is used in combustion. Now, butane's formula is C4H10, and in a straight chain, it would look like this. However, it has the ability to form a structural isomer, which is when two molecules have the same atoms but different bonds. And it's possible for all alkanes after butane. So after butane, it is possible for the second or third carbon in butane to be a branch off of the molecule. So for example, here we're looking at different alcohols, and we'll talk about functional groups later and how I know that these are alcohols. But here we have butanol, 4 carbons and a hydroxyl group. But that hydroxyl group could also come off of the second carbon in the chain, giving me a structural isomer of this. Or one of those carbons could come off and form a methyl group, giving me another isomer. Or they could all come off, giving me 3 methyl groups and the hydroxyl group, giving me a 4th isomer of 1 butanol. All of these will have very, very different properties from the original structure. Hydrocarbons can also form cyclic compounds or circular ones. The way you can tell if you're dealing with one is they will start with this prefix cyclo, and if they have only single bonds that end in ane. So for example, cyclopropane, pro means 3, so I have a circle of 3, and it's a straight chain, so all hydrogen, all single bonds. Now, the less carbons you have, the more strained these bond angles become, and these actually are far, far, far more reactive than their straight chain cousins. Again, that's when you have less carbons. The more carbons you have, the more stable the bond angles become, and therefore the more stable the molecule is. Generally, cyclic alkanes have the formula CnH2n. So propane would be C3H6. Oop, as I grab this for no reason. At low temperatures, alkanes are used as lubricants in plastics because they are generally inert. However, at high temperatures, alkanes are extremely combustible, and this is why they're often used as fuels. In the presence of halogens, one of the hydrogens or multiples of the hydrogens of a alkane can be replaced with a halogen, and this is how chlorofluorocarbons, also known as freons, can be made. Freons are extremely inert and often used as coolants. However, they are extremely dangerous to the environment as they tear holes in the ozone layer. Lastly, alkanes can undergo dehydrogenation reactions. Ooh, that was a mouthful. In which a hydrogen atom is removed and the hydrocarbon goes from being unsaturated, or so it goes from being saturated, where it has all hydrogens on its carbons, to being unsaturated, meaning it picks up a double or triple bond. Alkanes that have developed a double bond are called alkenes. They are unsaturated hydrocarbons, meaning that there is at least one double bond. Generally, alkenes have the formula CnH2n. So, for example, ethene, eth means two, so two carbons, so C2H, 2 times 2 is 4, H4. Developing a double bond changes the geometry of that carbon. So, for example, this carbon here, this first carbon in ethene, no longer has a tetrahedral geometry, it has a trigonal planar geometry, meaning all of the bond angles are 120 degrees. And also, because of this double bond, these molecules are now fixed into a very specific geometry. If you have the same structures on both sides of the double bond, it has a cis geometry. So for example, this methyl group and this methyl group are identical and they are both on the same side. If I were to cut this molecule in half, they would both be falling on the same side of the molecule. Therefore, this is cis 2 butane. 1, 2, 3, 4 carbons. So this would be but, and since I have a double bond, it'd be ene, so butene. So this would be cis butene. A trans geometry is when the substitutes for hydrogen are found on opposite sides of the double bond. So for example, this is 1, 2, 3, 4 carbons again, so this would be butene. And since the methyl groups are found on opposite sides of the double bond, this would be trans butene. Alkenes can also form rings, which are typically more stable than alkane rings, at least in the low side, the low number of carbons. So for example, cyclopentene, cyclohexene, they all start again with cyclo, but now they'll end in ene because alkenes end in ene, E-N-E. That double bond allows for some interesting reactions to occur. For example, you can reapply a hydrogen to an alkene to turn it into an alkane. This usually is done with some inert metal such as platinum or nickel. Used as a catalyst, hydrogen gas is passed over or passed through the alkene, and that hydrogen is picked up by both carbons to make it a saturated hydrocarbon again. It is also possible to do the same thing, but with a halogen. So this is called halogenation, in which a halogen is replacing the double bond for each of the carbons. If a hydrocarbon has a triple bond in it, it's called an alkyne. All alkynes have the suffix that ends YNE, or -ine. So for example, this hydrocarbon here has a triple bond in it. So 1, 2, 3, 4, 5, 6, 7 carbons in the longest chain. Therefore, this would be heptyne, Heptyne, because it contains at least one triple bond. Alkynes can also form aromatic rings, so this would be cyclo and 6 carbons, so cyclohexene. The triple bonds can be broken in either of the substitution reactions stated before, so halogenation or hydrogenation. Alkynes that form aromatic rings are typically more reactive than alkenes. And it's through these triple bonded cycloalkanes that allow us to form functional groups or add functional groups to a benzene structure, which remember is 6 carbons. So if you haven't seen that before, don't worry, you'll see it soon. And the next video will be on functional groups and how to determine what exactly each thing is named. There will be a video on nomenclature. So good things